Hello, everyone. Thank you for joining us today. We're really excited to have you all here. We've got a really great presentation lined up. My name is Kayla. I'm here from the Acelab team, and we have Jason here from ATOS. So we're excited to get started while we let everyone join. I want to show you all where you can learn a little bit more about ATOS on Acelab. So you should hopefully be able to see my screen here. We are on ATOS's Acelab page here. So anytime you want to search and find a specific manufacturer, all you have to do is search their name in the search bar at the very top of the screen. So here on their page, you'll see we've got some basic information, contact information for Jason, as well as value propositions, videos, and then all of their products for you to explore on your own. You can click into any one of these tiles here to learn more about the specific product. You can also save it to your firm library for future reference. So we encourage you to check out their page when you have a chance and to just dig a little deeper and learn more about what they do. So I'll drop a link to this page in the chat. A couple other things to point out. We do have an AIA accredited course for you today. So we collected your AIA numbers upon registration. So you should already be good to go in terms of getting credit. But if you're worried that we don't have your AIA number, I'll drop a form in the chat as well so you can fill that out and make sure that we have your number and that you get credit for today's session. We will be doing Q&A towards the end of the presentation. So if you have a question at any point, feel free to just drop it in that Q&A button at the bottom of your screen. We'll get to those at the end. We will also be doing a poll during the webinar, so you'll see that pop up towards the end. If you're interested in getting more information from the ATOS team, you can fill out that poll and we will be in touch with you. And then we will also do a post-webinar survey. So encourage you to participate in all those. That's everything from my end. So I'll go ahead and pass it over to you, Jason.
All right, thank you very much. And thank you everyone who's joining us here today, sharing a little bit of your morning or afternoon with us. Today's topic that we are going to be covering is sustainable building envelopes. As a manufacturer of metal panel systems, we will certainly be focusing on those. For webinars, we like to start off with a little bit of commercial as people trickle in, so just bear with me here for a minute or so. But ATOS is a 60-plus-year-old family-owned business. Third generation of family ownership is in senior management now, working under their father and uncle, who started the business with working as children with their father back in 1963 in Rochester, New York. Today, ATOS calls Allentown, Pennsylvania home, but we also manufacture in University Park, Illinois, and Mesa, Arizona. And we have a sister company called Brightsmith Coaters that handles all the coil coating and post coating of metal products for ATOS. So like I said, 60 years of operation and still maintaining that family feel and service first approach, allows us to be a little bit more nimble and responsive than some of the other companies in this space. Overview, we're going to be talking about a lot of different sustainable concepts today, which will cover a variety of these products, but we're most well known for metal walls, metal roofing. We have a full line of perforated products as well. We excel at curved and tapered roofing, custom fabricated panels and column covers as well, insulated metal panels, which will be a part of today's conversation also, interior ceilings and soffits, and perimeter edge metal, your fascias and coping systems. Architectural accents, however you can dream it up, we can figure out a way to build that. Accessories such as snow guards, solar racking arrays, and secondary framing for walls and roof systems. On our website, and most of this is also hosted on Acelab's website, but a lot of spec assistance. We have 3-part specs and spec data sheets on the Acelab platform for all our products. CAD details are also available as well. BIM modeling and photo galleries for inspiration if you're looking for something along those lines. So we will jump into the conversation of sustainable building envelopes here. This is AIA credits and GBCI. The GBCI credit is self-reporting, so just please be aware of that. If you need that credit, you'll need the certificate from today to get that credit applied. So today we're going to cover a couple of different learning objectives, but we're going to learn about using metal cladding as a component to contribute to uh, the decarbonization of your building. A lot of times manufacturers focus on the front end, making sure we meet certain lead credit points, but we're also going to be talking about systems and concepts that will reduce the operational carbon footprint, which is a bigger part of the puzzle, really, at the end of the day. We're going to learn how metal wall panels can be used to take the solar energy and create preheated air, and what that looks like. Talk about cool metal roofing, and then other technologies with UV reflected pigments and above sheathing ventilation for roofing systems. A lot of times people assume a metal roof is hotter and less ideal than other roofing products out there. And we'll explain how, that is a reality, but also there are very easy ways to counteract that in today's metal manufacturing world. So buzzwords, you're all familiar with them. Probably the two biggest are the top two there, net zero, carbon neutral / carbon negative. And of course, coming out of the pandemic, health and wellness is another big learning topic for people in the built environment. Green building, I'm sure most of you are aware of this, but it's that design outcome focusing on environmental durability and resiliency through the building's life cycle, helping it with better siting, design, construction, operation, and maintenance. This is a holistic approach, not just, front-end design. It's looking at the building throughout that 30, 50, 100-year life cycle of it. In terms of building operations, we're building more and more. We are becoming a more and more populated planet as well. And, that will require more energy consumption to keep everything going. Based on our current trends, the Energy Information Administration outlook forecast from 2023 to 2050 a 40% increase in energy consumption globally. So that's a big demand. How we generate that and how we generate that in a cleaner method is also something that we'll be talking about here. So, most of you are probably familiar with the AIA's Net Zero Challenge for 2030. The International Energy Agency has a net zero by 2050 challenge, focusing on renewable energies as a part of the supply chain side of it, but then also how do buildings become more energy independent, independent through solar photovoltaics, wind, so on and so forth. So this slide here talks about the globally installed clean power capacity and electricity generation. So from 2010 to 2023, you can see installed capacity ticks way up on that exponential bell curve. For the solar photovoltaics, wind has been a steady climber as well. Hydroelectric, not at the same rate, but steadily creeping up higher and higher also. But this still falls woefully short of total electricity generation needed. So as you can see on the slide on the left there, that delta is basically made up by using fossil fuels, coal, natural gas, so on and so forth. And then energy consumed in the life of the building. This pie chart here it explains a couple of different things. So you've got transportation, which represents, we'll say, probably about 20% or so of it. Industry, which is the supporting manufacturing world that helps create buildings. That constitutes probably roughly 40% or so. And then building operation and construction, the actual construction process and the operation of the building over its life cycle constitutes the remaining 40% of the CO2 emissions. So, and you can see there, like I said, we focus mostly on the building construction and the front end design, getting lead credits and all that good stuff. But more than double is the building operation. And again, that's, comparing it from a 1 year construction cycle to a 30 to 50-year life cycle of the building. So focusing on that building operational side is something that's sort of overlooked, but very important. And then this chart here outlines the global warming potential by CSI division. You can see that concrete and metals are fairly environmentally unfriendly. Uh, we are a metal manufacturer, but we live in Division 7, which is thermal and moisture production. Division 9 finishes. We've got masonry in there is another big one as well. So a lot of that just has to do with the manufacturing processes and techniques involved in that. A lot of energy consumption in those three primaries, concrete, metal, and masonry. Here we're talking about renewable energy sources and how they are going to change and evolve from 2023 to 2035, and then the forecasted growth for 2035 through 2050. You can see solar is actually going to become a smaller part of it. EVs are going to be a bigger part of this as well through either photovoltaic highway systems that I know they're developing in parts of Europe and Asia, and even having cars that are integrated in with solar panels to keep them going without having to plug it in per se. So you can see there will be an evolution that we're going to experience in a very visceral way over the next 20, 30 years. So checking in now, we're just going to, reset a little from that context and background and shift into some of the construction products and techniques that will help us with metal cladding and designing greener, healthier buildings. We'll go through all these different topics here. It'll be, really good content for you, I believe. So hopefully you find this as informational as I think it will be to you. So first off, we're going to be talking about transpired solar collectors. So this is a system featuring a metal cladding element with a standard barrier backup system behind it. Um, now, and I'd imagine almost all of you are familiar with metal does a great job of conducting solar energy and heat. Anyone who's ever sat on a sunny day in a high school football stadium bleacher and sat down on that aluminum with shorts on, you know how warm that can get. So I bring that up because what we're looking at here is using that same principle in a building technology. So typically, when you have a metal wall panel installed on a building, the airspace behind it's back there for draining and back venting. But that air temperature behind the metal panel will typically be 50 degrees warmer than the outside air temperature. So I'm here in Ohio today and it's about 50 degrees. And if I was in a metal building, that means the airspace between the insulation and vapor barrier and the metal cladding is going to be somewhere around 100 degrees, which is quite warm. And what we want to do is take advantage of that free energy, essentially, as a part of the building system. So this system, as you can see, it allows air to pass through it. That's what's the transpired part of the transpired solar collector passing through. So we're allowing air to pass through these micro-lance perforations or conventional perforations to have air go back into that space. And then I'll switch back to the previous slide because it's a better overall diagram. Instead of having that be a ½ inch to an inch off the insulation and vapor barrier, we're going to pull it off somewhere between 6 and 8 inches and create a big air plenum back there of superheated air that you can then draw directly into your HVAC system. Now, the one caveat you'll see here in this diagram, there is a louver there. It doesn't have to look exactly like that. It doesn't have to be as prominently placed, but we did this intentionally because you do have to have a summer bypass louver. When your building shifts into cooling mode, last thing you want to do is be pulling in, 150 degree air instead of 100 degree air. So that's what that is about on that facade schematic here. Skipping ahead, here's a better graphic showing an actual installation, highlighting the summer bypass louver. You'll have a double lattice work of hat channels or Z-girts or something like that to fur the metal panels off the building envelope so that you can capture that air and that space behind it. Typically, the intake will be at the top. It doesn't have to be necessarily. We have seen systems where it's placed at the bottom or middle as well. But typically, you want it at the top because, as we all know, hot air rises. So the hottest air will be pulled up there. You want to leave a clear chamber there at the top to allow for maximum airflow as well. But the double lattice does a good job of providing that airflow so that you don't have these pockets that remain stuck in there. A lot of times we're asked about the backup system and what that needs to look like. It can be anything from a CMU or precast concrete wall to a conventional metal frame building built up with insulation and vapor barrier, or it can even be a insulated metal wall panel system behind the transpired solar collector. The insulated metal wall panels are great as a backup because they're fully non-combustible. So if you're concerned at all about NFPA 285, you don't even need to get into the fire-rated insulated panels. You can use the standard polyisocore panels to achieve your Class 1A rating for NFPA 285. So here's the crew installing the panels as they go. And typically when you're seeing the system installed, it's going to be what's called an exposed fastener system. Um, the name is, as it implies, you will see the screw heads through in the valleys in installing it to the girts there. The reason you go with that type of a product typically is because of the structural capacity that the panels have, so you can space out your framing a little bit further apart. But you can have any number of structural panels, concealed or exposed fastener panels, as a part of this system. As I mentioned earlier, you'll typically see this spacing somewhere between 4 and 8 inches off the barrier backup of the wall. Can be used on existing and new construction. You can also tie it into rooftop mechanical units or do a direct intake. Here's an example of a project using a concealed fastener system. It's the darker bronze black colored metal panels there. They wanted to have that specific look, and they went ahead and moved forward with that panel system here versus an exposed fastener product system. But with this, just because of the framing and everything, sometimes we're asked, how do we handle all the architectural details with trims and corner conditions and so on and so forth? And all of the same options available in a conventional single skin wall design are available in this system as well. Requires a little extra framing at the corners and stuff like that, but everything is achievable with this system that you would otherwise get in a single skin application. So for the HVAC system, this air is connecting straight into the air handlers and reducing the load on the heaters. So instead of, like I said, in the winter, pulling in 30-degree air, you're going to be pulling in somewhere around 80-degree air temperatures, which is great. That requires less energy to heat the air up and reduces the wear and tear on the HVAC system itself. You can have it in air makeup or heat recovery units as well to further enhance the efficiency of the system. Uh, Here is an example of it being installed with a rooftop mechanical system. Now, the diagram on the left shows a big bump out there. That's just for effect, not in reality. It would just be a straight wall system up, but connecting through there into the RTUs and then blown into the building from there. The only issue here is that you will have to insulate all your ducts from the wall intake to the RTU to minimize any temperature loss. So that does make it a little less efficient, but still a very viable application in this regard. And then usually what you see is more of a standalone system where you're directly intaking it into the building. The picture here on the left shows that blue duct, which is a pneumatic sock. So that's one of those ones that's hanging up there and inflates when the air is blowing through and just collapses when it's not. Those are really great for large voluminous spaces and like distribution centers and warehouses and garages and things like that, because they send the air out in a very diffuse ambient way rather than blowing it in hot spots, every 10 to 20 feet on center. So this allows the air to get out there in a more ambient method as well. This slide right here, I like to call the most obvious slide in AIA presentation history. So when you're dealing with a solar collector panel, you want to have it facing south for the most part. East and west, southeast, southwest are all good. You can see the breakdown there. You're never getting less than 70% of the maximum solar irradiance, which is still pretty good. But if you're in the 90 to 100% range, that's optimal. But the other part of this that I wanted to mention is a lot of times you'll want this building to have some sort of design continuity all the way around it. So you can have the same panel system, same color, installed as a conventional single skin on the north, east, west, and just have it be active in certain areas with that depth. So it's very easily something that can be isolated into certain pockets, and then you can still have a conventional construction up there for the, sorry, dogs. Um, but you can have the system in those isolated pockets and then have a conventional wall assembly throughout to keep you a little bit more aligned with the budget. This isn't a budget breaker typically, but it will be somewhere between 10 and 15% above a conventional wall assembly. Mostly that's tied into the software package you get and the additional framing required there. For the ventilation air requirements, it is determined by ASHRAE 62 code for CFM, that's cubic feet per minute. And that will be dependent on these four categories here. So usually the first thing that we establish is the collector size, meaning how many square feet of surface area of material do we have to collect the solar energy with. From there, that will help us determine the porosity and the plenum depth in conjunction with the fan size. I am not a mechanical engineer. I'm not going to get any deeper into the weeds than that, but usually there are mechanical engineers available with manufacturers that provide these systems to walk through those steps. Another benefit of this system is heat stratification or destratification. So a lot of buildings in the United States, we blow hot air in at the top, and then we're down in the occupiable space down below. So anything that has high ceilings is fairly inefficient in terms of delivering that heat to the people that need it, because it's automatically going up to the top. So you'll have very warm air and towards the ceiling, and then you'll have that temperature where the thermostat and the person is what you want it to be, but you're creating a very inefficient system that way because all that hot air is going up first and then eventually getting down to the occupiable space. One way to use a transpired solar collector to combat this or to do heat destratification is to bring it in and blow that free warm air that you're getting up at the top, and then it allows your other heating systems to work more efficiently as well, creating a destratified heat source for you so that you can allow the other system to focus on just heating the occupiable space. Typical daily operation. This is an example of the sort of control board that you would see with the building. As I mentioned, there's a software package, comes with real-time modeling, can even be used on the front end for financial assessment on your return on investment and everything like that. But here you can see 25-degree air temperature on a winter day in January, but the fans are pulling in around 74 degrees, so right at that 50-degree delta, basically. This is for a manufacturing space, so the room temperature is 54 degrees. Ceiling temperature is 56 degrees, keeping it cooler because you've got active working conditions here. For the paint, this might also be a runner-up for most obvious slide ever, but darker colors are better for, this type of a system. Black, bronzes, dark grays, dark blues, greens, so on and so forth. The darker the color, the better the performance of the system. And that will get you into that 50-degree Fahrenheit temperature delta. There is a select low emissivity finish that's relatively new in the market because it has such a low emissivity, which is about 5%, meaning energy re-emitted back after the panels absorbed it back out into the atmosphere. It's only re-releasing about 5% of the energy it absorbs. So a lot more thermal energy is being transferred back into the airspace, and this can get you up to a 90-degree temperature difference. The only other thing I'll throw out here is with these systems, you see, we've got two pictures here that show clearly the panels going all the way down to grade, basically. In the right instances, that's fine, but certainly bear in mind that these will be quite hot, especially the select. So you want to just bear that in mind in terms of public safety as well when designing this system. The low emissivity select finish has a collector certification required by ICC SRCC for the North American market. It's being used pretty widely throughout Europe currently, and a little bit more in Canada, but it does go through extensive testing, and we can provide that information if you are interested in reviewing that. So here's a picture of a transpired solar collector. Not sure exactly what this is, but I believe it's a self-storage building. So they were using it to keep that building, locker building in a relatively comfortable temperature state. It does come with energy modeling and financial assessment through RETScreen, which is the software package that comes with the system as well. It's used in a wide array of applications. Usually we're seeing it in distribution centers, warehouses, and so on, buildings like that. But we are seeing it being used more and more in Department of Transportation projects for maintenance facilities. Local and regional transit authorities are using as well in their bus maintenance facilities. And then also fire departments really like it. In the lower left-hand corner, that is a fire department that has a fairly sustainable design. You can see some of the solar PVs on that, but that tower sticking up is clad in the transpired solar collector, bringing in warm air directly into the hose dry tower. So they they coil up their hoses and then drape them through that tower to let them dry out. That warmer, drier air, they found extends the life of those hoses by 5 to 10 years because it helps prevent the dry rot through conventional heating. So another benefit there as well. Another area where you will see it being used a lot is in agriculture. Anywhere where you're drying crops, if it's tobacco, coffee, cocoa, even marijuana, with many states doing that as they are nowadays. Very viable technology in those types of industries as well. And here you can see a very small portable urban spice drying tray that was done down in Colombia. So you can use it in little bits like that, but normally we're seeing it more and more on large scale buildings. Here's a brief case study for you showing the transpired solar collector. If this was a live format, I would ask to make sure everyone's paying attention if you can identify which of the 4 bays is active. But since we don't have that option here, it is the 2 bays flanking the center glass atrium portion. You can tell if you look closely, you can see the 2 summer bypass louvers there. That's the giveaway on this building. But low ventilation air requirement. Primary objective here is just for space heating. There are 2 fans, as I indicated, with the 2 bays, 9,000 cubic feet per minute capacity for each. And we have roughly 3,600 square feet of solar collectors. with a dark bronze color. 16 degrees southwest is the orientation of the building. And the results are that the primary heat source is used minimally throughout the winter. Total annual heating cost of $150 for this building, which is around a 55,000 square foot manufacturing facility. On a sunny day here, this is I believe in a January temperature range for this facility, but you can see here you've got a number of lines. So the magenta line is the room temperature. What's the indoor air temperature? Then you've got the red line for the fan inlet temperature. So that's the air behind the transpired solar collector. The blue is the outdoor air temperature. And then the gray line there is the inlet air velocity, meaning is the fan on or is it not? So you can see here essentially an inflection point where the red line crosses the magenta line, and then all of a sudden the gray line kicks on and you start the active portion of the day. So essentially you need that fan inlet temperature to be above the room temperature, obviously, for the system to work. So in the winter months, you do have a shorter window, but you can see it operating on and off all day. You can see dips in the red corresponding with the fan activity shutting on and off. And then at, probably what, 6:30, 7 o'clock, it turns off again. So this is just indicative of how you can monitor and assess the viability of the product. And you can see, that delta between the red and the blue line grows throughout the day. And that, right there is roughly at the peak, that 50-degree temperature delta. There are a lot of government incentives available for this at the federal level and the state level. I know people here are in a variety of states, so the best resource for you is the website dsireusa.org, and that will help you find all sorts of state, federal, and local tax credits that you can get for using this type of a system. This will also help contribute to a faster payback period. So green benefits to the system: converts up to 80% of the sun's radiation into non-polluting warm air, cost-effective way to meet code requirements for ventilation. So if you have a high air exchange requirement space, say a lab or something like that, in the winter months, last thing you want to be doing is bringing in, 30 air exchanges in a cold weather climate per hour, when you could have this system bringing it in at a higher temperature. That really helps make a major impact for indoor air quality, as well as your financial side. And it has also been found to improve indoor air quality as well. That air being superheated tends to be cleaner, drier air than you're otherwise bringing in through your standard intake vents. Wide array of LEED credits available here. This is still based off of LEED 4.1. We have not seen the latest and greatest on LEED 5 yet, but these are indicative of what the credits are currently available for LEED. Now moving on to the next topic, which is continuous insulation and air barriers, and how this can be a part of your sustainable envelope. So really, we're going to focus in on the continuous insulation. That's a very important part of this. Making your building as well insulated as possible ensures that your HVAC system is running as well as possible as well. So ASHRAE 90.1 is the code that is governing this for commercial and residential buildings, requiring insulation across all structural members without thermal bridging. It says without, but really it's with minimal thermal bridging. That there are percentages that are allowed in that space with the insulation. And then the other big part of this, the rain screen system, is the air barrier. And that is what allows, that's your final line of defense, essentially. Your rain screen's out there to reject most of the rain. The airspace will allow that to drain out, but your air barrier is your last line of defense between the indoor and outdoor space. We have seen in the industry a pretty big shift away from impermeable and semi-permeable weather barriers into fully permeable. So think of these almost as a Gore-Tex type rain jacket. So I'd imagine most of you have one of these or have experienced one where it's going to reject all the rainwater trying to come, landing on you, trying to get you wet. But it's still breathable so that your body heat and your vapor escapes through it, so that you're not becoming uncomfortable as you're remaining active in those types of elements. So that is essentially where we are with the weather-resistant barriers in building technology nowadays. So this is an axonometric exploded showing the conventional built-up assembly of a rain screen. You've got your metal studs, your exterior sheathing, your air and vapor barrier, your continuous insulation, then your metal girts, and your exterior cladding. So a lot of elements coming together, a lot of connections required. How do we minimize that thermal bridging, that heat flow through from the exterior cladding to the structural members? There's a couple different ways. Don't worry, we're just teasing you with that. We'll get into it. But first, there is the ASHRAE climate map here. Breaks the U.S. down into three climate zones: marine on the west coast, B, which is dry in the mountain west into the plains a bit, and then you've got firmly half of the country in the moist, humid area. And then you've got the different climate zones going from 0 all the way down to 8. So, and we are in the very unique position here in the US of having almost all of those. So, we've got 1 through 8 in the United States. So a wide array here to consider. In terms of insulation, you essentially have three products that you can choose. Well, three types of products you can choose from. Mineral fiber, so any type of 1 hour, 2 hour, 3 hour fire rated wall will require mineral fiber, more commonly known as rock wool or something like that. Then you've got your rigid foam, your polyiso blue boards. You can get them laminated in Sims panels, so on and so forth. But that is your other methodology. And then last is the insulated metal panels. And that is encapsulated polyisocyanurate. And we'll get into all these specifically here. But talking about the cladding effects and reducing that conductivity of the thermal energy from the exterior to the interior, a couple different ways you can do it. You can use engineered subframing, which is one of the better ones. This is sort of a basic wall assembly hack that is used. So you're attaching your panels to the front face of this girt, and then you have pre-drilled holes oversized on the front face for your driver head, and then a hole on the back for the pilot for the screw that goes through. So you've isolated it to a certain extent here. Energy can certainly still flow through that channel through the hardware, even though they are thermally isolated. There is still some thermal energy that will transfer through this. Going through the insulation will help isolate it further, but the best way to do it is, in this style, is a thermostat fastener. So it has a thermal break in the screw head and will help you meet that ASHRAE code. Other thermal bridging isolation members that we like, you can use Nightwall. They're definitely one of the better providers for engineered subframing, especially in fire-rated wall assemblies. Smart CI is another great manufacturer that uses a pultruded fiberglass extrusion that integrates in with the polyiso boards. It's the green bit there at the bottom center. So that up leg is what you would attach to the building structure or sheathing. And then the front face down leg is what you would attach your girts and or cladding to. And then you can see in the sort of center of the 5 images here, a little plastic shim. That's an above sheathing ventilation shim, but it is thermally isolating as well. So, we talked about the other styles of insulation, but IMPs, insulated metal panels, as a barrier backup panel system. So a lot of times insulated panels are used as that just all-in-one cladding element, but they can absolutely be used as a barrier backup system as well. It's an alternative to a multi-component system. And what this does is kind of, a layered effect of efficiencies. You're going to get a more robust insulation performance per inch, a better R per inch performance. You're going to have a longer lasting product. You're going to have something that installs quicker and requires only one mobilization versus multiple mobilizations. So an IMP as a barrier backup element will replace your sheathing, it will replace your vapor barrier, and it will replace your continuous insulation. So it's at minimum 3-in-1 for you right there, which is great. So getting into this a little bit, here's a couple of examples. I will say IMPs are sort of limited products, especially if you're considering them as the finished element, which these two pictures show. So panels are going to be typically 3.5 feet wide. You can get some architectural fabrication and integrated into these panel systems, but they're very wide. They have a different monolithic scale to them than a lot of the other panels that you might look at in metal skins. And then the other thing is, you can see here from these two pictures, virtually no shadow lines, no depth to the profile or corrugations. That is done intentionally because your R value is based off the minimum of the panel thickness, not the average, not the thickest, but the minimum. So if you put in a lot of ribbing, you're buying and paying for a lot of insulation that you're not getting the benefit of. So to that end, insulated metal panels typically have very minimal striations and fluting in them to help, make sure we're getting the most efficient product as possible. They are filled typically with a polyisocyanurate core. There is polyurethane foam cores out there still, but almost all of the industry has shifted to the polyisocyanurate cores. Very easy to install, double tongue and groove assembly. For the panels. I was hoping there was a picture there, but you can kind of see it in the diagram. Here's a double tug and groove where the panels come together. Each one of those grooves is filled with non-skidding butyl sealant, and that's what helps you achieve your vapor barrier in the product as well. So used in a wide array of building types, but again, large volume spaces, quick erecting things like warehouses, airport hangars, office buildings, manufacturing facilities, cold storage sites, so on and so forth. Seeing it being used a little bit more frequently nowadays in sports complexes. Universities are adapting it as well. The only thing that I'll say in terms of using it in all these different building typologies is that this product system really only works with metal frame or concrete frame buildings. If it's a wood frame building that's not mass timber, you're going to have issues because that timber is going to dry in and compress, but the metal panel is not going to experience that. So you're going to have issues trying to integrate this into a wood frame building. But insulated metal panels are, they help reduce the overall heating and cooling costs by preventing a better, more robust insulation around your building, reducing the wear and tear on it, providing higher levels of indoor air comfort, and helps against fire protection as well. This chart here, I know it's a little blurry, but it essentially breaks down the three major insulation types. So you've got your extruded polystyrene or expanded polystyrene, that's your blue board, your spray foam, those types of things. R4, R5 per inch is pretty standard with those products. Your mineral fibers, your rock wool, your fire rated insulation, R3 per inch. But with a polyurethane or a polyisocyanurate encapsulated, because it's encapsulated and compressed during manufacturing, you've got a closed cell structure which enhances the insulation values. R7 per inch is the low end. Most manufacturers are saying R7.5, even up to R8 per inch. I always like to be a little cautious here so that we don't get caught short, but a much better performance out of this system than the others that are out there in the market space. Insulated metal panels are structural in nature, so you can space your framing out further apart. There's no universal truth. It depends on a variety of factors, but we'll say 6 feet is a pretty standard and safe span length for these panels. As I mentioned, they do meet NFPA 285 fire code, and with the mineral wool core, which is available, you can meet those 2-hour, 3-hour walls as well. Enhanced thermal properties. And water penetration and air pressure differentials are accommodated by these as well. So every time insulated panels are installed on a building, full set of shop drawings and structural calculations are provided to address all of these concerns with structure and pressure differentials. This is the diagram I was looking for a little earlier, but shows more clearly the double tongue and groove assembly. The red highlights there are the non-skidding butyl. This is applied in the field to maintain, just fresh conditions and everything, and dirt and debris don't build up in those grooves before the panels are installed together and the butyl starts to cure. The other line in the diagram is the blue line, and that represents the loose clips that are shipped out with the system. Loose because we never know exactly where the spans are going to be. They're about 2-3 inches long, and they come with 5 pilot holes in them. Usually you're using just 2 or 3, but 5 are provided for that top end engineering, just keeping it standard and easy for everyone. There are insulated metal roofing products out there in this world too. These are great. They do come with the sort of same design limitations, minimal ribbing and fluting, and 3.5 foot wide modules typically. There's a couple different seam locks. The one you see here is a T batten style. So you've got just the one tongue and groove connection at the bottom, and then you have your clip coming up, which actually integrates in with the seam and the batten clip at the top. The batten clip is applied with more non-skinning butyl at the interlock, and then is snapped on and cures in there. This is an assembly that does require a mechanical lock. So a seamer would have to run up and down the roof panels and crimp that in for full weather tightness. And these products are almost always rated to go all the way down to a 1/2-12 roof pitch. So pretty low slope roofing. But as a result, that seam is going to be at least 2.5 inches tall. And we've been talking about it mostly as a barrier backup system, but this is what an IMP can look like on the high end with architectural features integrated into the product. I would imagine if none of you really thought too long and hard about it, you might think this was a big ACM installation, but this is in fact all insulated metal panels. So trimless reveals with gasketed trim conditions there for weather tightness, factory formed mitered corners, multiple colors, as you can see in the sort of secondary bit in the back there, funky geometries that are cut in the field. But you can do a lot of different things with these products. The other great part about insulated metal panels is, besides the thermal efficiency and performance, is how quickly it's erected and dries in and insulates your building. You can install them horizontally or vertically. Vertically, as you can see here, you do need to use one of those vacuum lifts because strapping just won't work with it in that direction. But that allows you to swing it into place, integrate it in, and lock it in with the next panel, and then use the clips to install and attach it to the structure behind. On average, a building that features insulated metal panels is either the primary cladding or the barrier backup system is able to compress its schedule 5 to 7 weeks versus a conventional built-up assembly. That's mostly achieved through reduction in the mobilizations and getting material on site and working your way around the building. Like I said, you're done all in one fell swoop with sheathing, insulation, and vapor barrier. And then the other part of it is once that building is dried in and insulated, your interior trades can get to work straight away. So they can't start work until that's all completed. So if the sheathing's up, your electrician and your plumber can't get in there until the insulation and everything else is up. So again, it helps compress the schedule in multiple ways. Here are a summary of the LEED credits, again, 4.1. But a lot of different LEED credits that you can earn points using insulated metal panels as cladding or barrier backup systems for. Next up is cool metal roofing, and I'm going to try and breeze through this so that we leave a little bit of time for Q&A at the end. But essentially, everyone thinks about metal like we talked about with the transpired solar collector, being hot, having hot air, transferring that into the building. There's two categories here, thermal reflectance and emittance. Reflectance is the solar energy that's just bounced directly back out into the atmosphere. And then there's thermal emittance, what is absorbed and then re-radiated out later in the day. So solar reflectance and emissivity are measured in decimals or percent of the the overall performance here. And it's mostly collated into a manufacturer's color chart, which will feature what's called a SRI, or solar reflectance index. So with cool pigment technology, it's really allowed for darker colored metal or darker colored paints to be used in this space and be more efficient in terms of thermal performance in construction and reducing that. So cool walls, has brought this technology into cool metal roofings, minimizing that heat gain into the building. But with all of that being said, there is still thermal transfer that can occur. One of the best ways to eliminate that almost altogether is by using above-sheathing ventilation shims, which we talked about earlier on during thermal bridging. So it will contribute thermal bridging, but with a vented eave and a vented ridge, you create a chimney effect and just let that air flow through. So any hot air is just immediately vented out of the roof assembly and reducing that transfer. Here's an image of it being used as a wall panel support and on our roofing system. So these are only 3/8 of an inch. So, there's not enough flex in that panel as they're spaced out 18 inches, 24 inches on center with the clips that you're going to get any permanent set by walking on your roof. So it's not going to compromise the structural performance of it whatsoever. It's just creating that airspace there so that you can allow air to move through. And like in the wall technology with the weather resistant barriers, you are seeing your underlayments in the roofing world become more and more semi-permeable or fully permeable as well. So allowing that vapor that's coming from the inside of the building to escape and not trapping it with a metal roof panel right on top of it is a really great feature. I'll touch on this briefly, but California has Title 24 building code. So already in California, you had to have a non-combustible roof. Now you have to have that roof, if it's metal or tile or whatever, with a 1-inch airspace added to the roof deck over the attic. So what they were finding was embers would sit there, and yes, the roofing product wouldn't combust, but enough embers would collect, transfer enough heat down that it would cause the substrate or the sheathing to combust. And that's what contributed to some of the wildfires back in 2020, 2021 in California. So they have since a modified code to allow for this. I'm not going to say this will be universal, but as climate evolves and you're seeing wildfires in the Carolinas and Georgia and even Virginia now, I'd imagine you're going to see more and more states looking at adopting something similar to this as well. The green benefits of cool metal roofing allows up to 40% less energy consumed than darker roofs, or what we used to be able to consider darker metal roofs with the cool pigment technology. So again, this is going to help homeowners. You typically, with metal roofing, we're associating it with residential more than commercial buildings, but it also works in the commercial space perfectly. Here's a number of the lead credits for you. A few other categories to talk about in terms of metal roofing: rainwater harvesting, where municipalities allow for it. It is a great way to collect water, non-potable water for gardening and so on and so forth. PVDF finishes, which are applied almost exclusively on metal roofs, are a chemical molecule or two off of Kevlar. So it sheds water incredibly quickly and cleanly. I mean, certainly there will be some dust and things that build up on the roof, but you won't get any of the toxic chemicals and other aggregates that you might get with, say, asphalt shingles. The other benefit of metal roofing, which is really cool, is solar ready roofing. And by solar ready, we mean, yeah, we can do it all day one, photovoltaics and metal roofing. But we realize that not every building owner has it in their budget to do all of that at once. So as long as we're aware of it on the front end, we can design and engineer the clip spacing to support that load. You can come back in 5 years, 10 years down the road, the roof will outlast the photovoltaics most likely. And as long as the system's been engineered for the loads that will be applied with these, you can come in with clamps that attach to the standing seams and then attach your solar array racking system to that. What this allows is a no penetration photovoltaic retrofit application. Again, this is only for standing seam metal roots, not all metal roots. There are batten caps and shingles and stuff that would not apply to this. But with standing seam metal roofing, you can absolutely modify, retrofit a roof with zero penetrations to accommodate photovoltaics. I know we're up against it, so I'm going to kind of breeze through here at the end. Last slide I want to pause on is Zero Code, a great modeling tool available to designers. I believe it's free for most architects, but it'll take into account ASHRAE and IECC standards and help you do a preliminary modeling analysis of your building design and highlight where it's being efficient, where it's not being efficient. So with that, I would thank everyone for your time today, and we've got a couple minutes here left to open it up for questions.
All right. Thank you, Jason. That was great. Yeah. Let's go ahead and jump right in. Folks, if you have any questions, feel free to drop those in now. All right. First, I've got what gauge options are available for each panel system.
So that will vary a little bit by panel system. The world that we live in, it's pretty standard to do 032 aluminum and 24 gauge steel on the commercial end. You can go lower, but that's not really recommended for commercial. And then on the higher end, 22, even 20 gauge steel. I see some 18 gauge steel and aluminum up to 050 in the single skin world. Beyond that, you start to get into aluminum plate, which can get up, from 063 all the way up to 1/8 inch or even 1/4 inch.
Okay, perfect. Next we have, what are the wind uplift ratings for your roofing systems?
So on our website, we have a variety of lid tables that do cover all of that stuff. We have Florida building product approval, so we can meet some of the more stringent uplift load requirements. Usually your worst is going to be at that sort of ridge gable corner or your eave gable corner. So roofing is usually divided into field, edge, and then corners. Corners are the most severe for wind loads. And there you might just space your clips closer together. It more comes down to the clip spacing than the product itself, to be perfectly honest with you.
Gotcha. Perfect, thank you. Next we have, can you provide design assistance for custom details?
Absolutely, yeah. That's something that we're going to say we're out of the AIA portion, but something ATES is very happy to provide. We place a high degree of emphasis on working with designers and helping them create their vision. So we have a full network of product reps that are direct and independents, and all of them are perfectly capable of helping you, establish some custom details to meet your project specific needs.
Amazing. Awesome, thank you. All right, and then next we have a question on what are your current lead times for standard and then custom products?
So it's a bit of a moving target, of course, but I would say somewhere around 4 or 5 weeks is pretty good for standard products. Might be a little less than that, but not more than that. Um, for custom, it kind of depends, but I would say probably somewhere between 8 and 10 weeks, unless we're talking about custom paint as well, and then that can push it out even further.
Mhm. Yep, good to know. All right, I think that is the last question we have for now, and we're right at time. So, any
Perfect.
final points, Jason?
I think I've said enough, but yeah, please feel free to visit our page at the Acelab platform and use the chat to engage with us with any questions you might have. And we will do our best to put you into contact with the local representative and get you the information you need.
Perfect. Okay,
All right.
thank you so much,
Thank you,
Jason.
everyone.
Thank you everyone for joining us. Yes, everyone have a wonderful day.